I'm pretty sure that we did. I put a bunch of asterisks around it, I believe. All right? It's the movement of ions that matters. I don't remember exactly how I worded it. It doesn't matter. It's going to say the same thing. The movement of ions that matters to membrane potential. Meaning what? Your membrane potential of a cell is going to be dictated by how ions move. Okay? Again, I can't begin to tell you how important that is. I'm going to say that at least a half a dozen more times in this lecture, probably more. All right? And I'm going to say it in my office when you guys come and see your exams as well, because there's always a number of students that forget and can't understand why on the exam they got a question wrong, and then I say these words. It's the movement of the ion that counts, and then the light bulb goes off. Oh yeah. Don't let that happen. All right? This is an awesome class. Maybe it won't. I'm hoping it doesn't. All right? And I'm going to show you exactly why that is so important when we get to some other things today. I'm going to reinforce that over and over and over again. All right, guys? So, that's resting membrane potential. There is a normal resting membrane potential in a cell. Now, some good news, and I don't remember if I shared this with you on Monday or not, but there's a number of things that you don't have to know for this exam. It's all on one page. I think that's page 144, I think. So at the top of that page, you should see the Golden-Hodgkin-Katz equation. You should see Nernst potential. You should see equilibrium potential, Nernst equation, all that stuff. Just cross it out because it's not on the exam. All right? I believe it's an entire page of notes. It's good. It would take me about an hour to go over that stuff. I don't have an hour. It doesn't matter. I promise you, you're not getting gypped on your education. All right? You'll still understand everything you need to understand, even without that information. I promise. All right? So that's gone. That's gone. That's gone. What's not gone is this. So we've established up until this point how a resting membrane potential is established. Do you think that resting membrane potential is the only membrane potential of a cell? Of course not. It changes. I'm going to show you how membrane potential changes in cells. All right? So how does membrane potential change? Well, we already know. How do we know that? Because I just told you right here. It's the movement of the ions that matters to membrane potential. So we're going to change the movement of ions. And when we change the movement of ions, we're going to change their distribution across the membrane. And when you change the distribution of ions across the membrane, you change membrane potential. What makes ions, what makes molecules move across membranes? Two things, right? What's the reason a molecule will move passively? What's the reason? A gradient. What gives the ion the ability to move? That's called permeability. So there are two things that will cause an ion or a molecule to move across the membrane. A gradient and permeability. Can gradients change? Can the concentration of an ion change? Of course it can. Can permeabilities change? Absolutely. So we're going to change membrane potential by changing either the concentration of an ion or the permeability of an ion. Those are the two ways that it can happen. And then we're going to explore that. Before we get into that one page that looks kind of nasty, I think it's page 145, and then the top of page 146, you see a whole string of things on those two pages. Before we get to the specifics of those pages, I am going to generically talk about those two pages. You guys are going to coach me through this, all right? So I'm going to draw a cell here. So here's a cell. I'm just going to ask you a simple question. Actually, you know what? I'm going to draw the cell a little bit smaller. So I'm going to draw two cells. Okay, so there's a cell. It's going to be the same cell, by the way. All right, that's a cell at time 1, and this is the same cell at a later time. All right, at time 2. They're both the same cell. All right? Now, we're going to have a cation. I'm going to call it cation A. That's a positively charged ion, by the way. I think we already know that. Cation A is moving into this cell. All right, and again, it's positively charged, and we're sitting at rest, so we're resting at this time. Okay? We're not going to worry about other ions, just this one. and what its influence is. And so, because of that, we're going to have a number of these cations stuck to the inner membrane, and it's going to, along with other ions, give us a normal membrane potential at rest. Okay? Then what we're going to do is we're going to change something. We're either going to change the concentration of that ion, or we're going to change the permeability of that ion, such that, and we'll give ourselves a visual, the same cation. More of it's going to come into the cell. That's why we draw the arrow bigger. Should I have more or less positive charges on the inner membrane now? More of this ion moves into the cell. More or less positive charges? More. Okay, so we're going to draw the same number as we did initially, because that is what it was at the beginning. Now we have these additional charges. Let's circle them so that we know that they're additional. What should happen to the membrane potential? Should it get more negative or more positive? More positive. So Vm equals more positive. It's got a special name. When you make membrane potential more positive, you are said to cause the cell to depolarize. That is a word on page 145. It's in bold, it's toward the top of it. You'll see it. It says depolarize or depolarization. Depolarize is the verb. Depolarization is the noun of that verb. When you depolarize a cell, you're making membrane potential more positive. Okay? Are we good? All right? That's just one example. I've changed the movement of an ion, did I not? I made more move. How did I do it? Maybe I changed the permeability. Maybe I made the permeability go up. Maybe I changed the concentration gradient. Maybe I made the concentration. By the way, what would I have done to the concentration? Would I have made it bigger on the outside or smaller to cause this movement to occur? Bigger on the outside. I could have increased. How could this have happened? This could have happened by increasing the concentration of cation A on the outside of that cell. Extracellular cation concentration goes up, it increases the movement into the cell. Could I have changed the concentration inside the cell? What would I have needed to do to cause more cation A to move into the cell? Do what to the concentration inside? Make it go down. And keeping the outside the same. So that, or decreasing cation A's concentration inside. What would I have done to the permeability? Increase the permeability of cation A. That would also cause more cation A to move inside of the cell. Okay? We're changing the movement. It's the movement of the ion that counts. All right? And when I give you a specific example, I'm going to repeat that because I know the knee-jerk reaction is going to be, you're going to tell me something after I pose a question to you, and many of you are not going to say the right thing. Okay? Which is okay. I don't know, maybe none of you will. Just in the past, students in unison said the wrong thing. All right? We'll just see what happens. All right? So that's one example. Let's do another one. Okay? A cell. Same cell, later time. All right? Time 1, time 2. Okay? We're going to do an anion this time, a negatively charged ion this time. So we're going to have anion A, both inside and out, then we don't have to put them both. Okay? And anion A is going to be moving into the cell, just like cation A moved into the cell. So we're going to have a number of charges on the inner membrane, and we're going to have a nice resting membrane potential. And then what's going to happen in this particular case is, we're going to change something so that less anion A moves inside of the cell. Okay, so we're going to put the negative charges that we had to begin with. 2, 4, 6, 2, 4, we got 6. Should I add more negative charge or get rid of negative charge, given the new environment? I have less anion A moving inside of the cell. So should there be less negative charge on the inner membrane or more? Less, right? We're changing something from rest. What's the change? Less movement of anion A. Let's make it perfectly clear. Let's just make this arrow really big so we can see that there's a clear difference. So now there won't be quite as many negative charges. What should happen to membrane potential? Should it get more positive or more negative? It should get more positive. If there's less negative charge on the inner membrane, membrane potential gets more positive. So, Vm equals more positive. What do we call that again? The cell is depolarized. Does that make sense? So you can depolarize a cell by making more positive charge go in. You can depolarize a cell by making less negative charge travel through the membrane into the cell. Two examples. Okay? How could we have done this? Decrease the concentration of anion A on the outside of the cell will cause less to go into the cell. Or increase the concentration of anion A in the cell, that will make the gradient smaller. Or what to the permeability? Make it go down. So the permeability of anion A, make it go down, less moves. All right? We're changing the movement of ions. Are we good? So the key to knowing what happens to membrane potential is three things. Number one, knowing the charge of the ions is important. That's very important. All right, knowing the charge, knowing which direction it normally moves. Okay, and knowing what the change is going to do as a result of those two. Okay, is going to allow you to ultimately know what happens to membrane potential. So this example that I've given you here, next I'm going to do one more. Okay, and then we're going to go on to that page. Cell at two different times. Time one, time two. We're going to do a positively charged ion. So we're going to put cation A inside the cell, and this time cation A naturally moves out of the cell. So because of that, a whole bunch of positive charge on the outside of the cell. All right? In this particular case, I'm going to cause more cation A to leave the cell. So I'll make the arrow nice and big. Let's make this one a little bit smaller so that we can clearly see that that's what the change was. More is moving out. Should I put more positive charge on the outer membrane or less? I should put more. So I'm going to put the same number that were there initially, and the new ones we're going to circle so we know what the change was that occurred. So more positive charge is now on the outer membrane. Tell me what happens to membrane potential. Does it get more negative or more positive? It gets more. Got a 50-50 chance. I can't hear anybody say anything. More negative. Beautiful. The outer membrane is more positive, right? Which means the inner membrane is more negative, correct? And when we measure membrane potential, it's inside the membrane versus out, not out versus in. So membrane potential equals more negative. By moving positive charge, but we're moving it out of the cell. We moved more positive charge in this particular case, but the positive charge was going into the cell. We moved more positive charge in this particular scenario, but it was moving out. So we had the complete opposite effect on membrane potential because membrane potential is measuring inside versus outside. That also has a name. It's called hyperpolarize. Okay, now those of you that have taken other science courses, the definition of hyperpolarize and depolarize are different than physiologists. I don't know who changed it, whose idea it was to change these terms and how they're defined, but it is what it is. And in this class, we are physiologists. So, as physiologists, depolarize means membrane potential gets more positive, hyperpolarize means it gets more negative. End of story. That's how it is. Okay? How could this have happened? How can we remove more cation A? How do we transport more cation A? Well, we could have decreased extracellular cation A concentration. That would have done it. Or we could have increased the concentration of cation A on the inside of the cell. That would have increased its movement. Or increased the permeability of cation A. How do you change the movement of an ion?